All right, guys, so I put up a little bit more extra credit problems on WebAssign if you watch a couple more of those 3 blue, 1 brown videos. There's 2 more videos I put up that you can watch and answer the question and get a few extra credit points, or 2 to be precise. And I came up with another sort of extra credit thing. You know, students are asking me about extra credit, like, oh, Professor, can you give us more extra credit? Like, that's all great and all, but don't rely on that like to save your grade in the class. You can spend like 20 minutes watching one of those videos, or you could spend 20 minutes studying for the final, and the 20 minutes spent studying for the final would probably have a lot bigger impacts on your grade. I'm just putting in all these. One of the main reason I'm putting in these sort of extra credit opportunities is to try and inspire interest and show you guys some of the cool stuff that can be done. Because sometimes the stuff that we do in here can be kind of dry and boring, and you wonder am I even ever going to use this? And you don't get to see some of the really cool things that get to be done. Like the material that we're talking about right now is actually some of my favorite calculus material. There's just so many cool problems that are involved with infinite series and sequences. Like I'm looking at all these problems at the end of the problem section for section 10.2, the section that we're on now. And there's so many cool problems involving walking a zigzag path along a triangle that involves an infinite number of terms, or let's see, what else do they have there? Like adding up an infinite number of really small triangles, or Archimedes' method for calculating the area inside a piece of a parabola. There's all these neat little problems, and I want to just give them all, except we only have a limited amount of time, so I can't get into all that, but I'll try to get into some of it. And I put up one problem now on GradeScope. So this is something new that you guys haven't seen yet. I went and asked the department to get us a grader because me and the TA, we don't have time to grade all these potential submissions from you guys. But there's a thing up on GradeScope right now to do this. It's to figure out what is this? Root 3 square root of 3 times the square root of 3 times the square root of 3 ... This infinite nested sequence of square roots. And this actually converges to a number. So you'll read the problem, you'll see it. You have to look at an example that's in the textbook that I wanted to do in class, but I didn't have time. So that's kind of why I'm giving this as this extra credit problem. So you'll go do this problem, scan your solution, and submit it on GradeScope, and I'll have the grader grade it. And it'll be worth, there's 3 parts to there's 3 things you have to prove in the problem, so they'll each be worth a point for 3 total. So yeah, go on GradeScope and check that out. Okay, so now we can finish up with 10.2 series. One of the last things I was saying about series, let me remind you of what it means for a series to converge. So when we're adding up this infinite number of terms, we define these partial sums, which are a sequence, and we already have defined what it means for a sequence to converge. i.e., so here's the notation. If I just write the summation symbol and some term, we say that this converges if the partial sums, which we usually use the letter S for, and I'll use, how about a subscript capital N? So that's the sum from little n equals 1 to capital N. So if this sequence converges, and you might have noticed that we sometimes use different subscripts for sequences. Like here I'm using a little n, here I'm using a big N. Sometimes we use K or M or I or J. Doesn't really matter. It's just an indice or a placeholder, so don't let that mess you up. Okay, so what am I going to do next? Okay, so after we learned about convergence of sequences, one of the things I did was give you some properties of limits, like how you can add them together, or multiply by a constant and so forth. So those properties still hold for sequences. So here's a few, those properties still hold for series. So here's some series properties. So if AN and BN both converge, then so do their sum and difference, and they converge to the sum and difference of the limiting values. So I'll just write that as you can add the two terms, and you get exactly what you would hope to get. You can basically interchange this sum with this one. So, and again, crucial that we need both of those series to converge in order to be able to apply this. And I said add, we can also subtract too, so I'll put a minus sign there. That's one property. A second property is you can multiply through by a scalar. So the sum of C times AN is C times the sum of AN. So I could prove both of these, but I think in the interest of time, I won't. It's not that hard. I'm going to prove some other much more interesting things today. Yeah, okay, so now I'm going to get finally to that big example that I was talking about, like, since we started this chapter, which I did that example using the pizza. I don't know why I keep coming back to pizza, but I was saying, like, if you ate half of a pizza, and then you ate a quarter of a pizza, and then you ate an eighth of a pizza, and then a 16th, and consecutively ate smaller and smaller slices. After eating an infinite number of slices in such a way, how much pizza will you have eaten? One whole pizza. So that kind of jives with our intuition because, well, like, what else could it be? You never eat more than a whole pizza. You certainly don't stop at any point less than the whole pizza. That only kind of leaves one possibility, which is that after eating that infinite number of slices, you've eaten the whole pizza. But now let's show that mathematically. So to do that, I must define a geometric series. So AN equals C times R to the N is a geometric sequence. So if we just add up the terms of a geometric sequence, C times R to the N is a geometric series. And it's one of the unique. It's one of the only ones that we can get a really nice compact formula for. So there's this really cool trick for doing it. We can actually calculate an explicit value for what a geometric series adds up to. So let me now demonstrate the proof of this to you. And I actually remember the first time I saw this proof, and it always stuck with me because I thought, oh man, like that's such a neat trick. Okay, so here's how it goes. Let's write out C, the first few terms, and let's start it, say, at 0. It doesn't really matter, as I will show you. Actually, here, no, let me not put these on here, but let me put them on here. So let me start writing out terms. The first one is C, and then CR, and then CR squared, and on and on. But as we know, as I reminded you, if we want to talk about the convergence of this thing, we need to look at its partial sums. Man, who calls people anymore? Jesus. So the partial sums will be, I'll only go up to the nth term, so S sub n will be the sum of CR to the n from n equals 0 to capital N. So S sub n will equal C plus CR plus CR squared plus dot 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 plus CR to the n minus 1 plus CR to the n. Okay, no problem there. Now here's the trick. Let's multiply this by the common ratio, R. So if I multiply everything by little r, R times S to the n is, well, let's just put an R on every single term. So I'll get a C times R. This will be CR squared, CR cubed. This becomes a CR to the n, and this becomes a CR to the n plus 1. Okay, great. And if you look at this for a second, you might notice that these two expressions have a lot of terms in common. In fact, almost all of them are the same, except, right, like this CR, same as this, CR squared. The next term would be a CR cubed, CR to the n. So if I subtract this minus this, so on the left side, I'll do Sn minus Rsn. Then I get to cancel a whole bunch of terms. So, right, these two terms cancel each other out. These two terms cancel each other out. This one and whatever the term is right here would cancel each other out. These two, or maybe I should, yeah, these two cancel each other out. These two cancel each other out. Everything cancels out except this minus this. C minus. So that's kind of the cool part, is I was able to cancel all this stuff. And now I can just pull out that number Sn. Sn times 1 minus R is equal to C minus C times R to the n plus 1. So Sn is C minus C times R to the n plus 1 over 1 minus R. All right, so we now have a formula for the partial sums. This is a useful formula unto itself. All right, so let me just write it one more time. C plus CR squared plus C times R to the n is equal to C minus CR to the n plus 1 over 1 minus R. I'm going to give you a few formulas that I'm going to circle here, or that I'm going to put in a box because they're all kind of important. So, great. In particular, by the way, A lot of times C is just 1, to be honest. And if it's not 1, you can just factor it out. So if C is equal to 1, which is just a particularly common situation, 1 plus r squared plus r to the n is 1 minus r to the n plus 1 over 1 minus r. This is a very useful formula. Okay, that's great, although I still haven't answered the question of what the infinite series converges to. This is only a finite sum. This is just the partial sum. What we really want to know is what happens when we let the terms go off to infinity. So now I can do what I said here is take the limit, right? Like, to remind you of what it means to say that this sequence converges, i.e. the sum from n equals 1 or 0, wherever you start from, is the limit of the partial sums. So in order to find what the infinite series is, I need to take the limit of the partial sums. Can I do that? And this is the expression right here I need to take the limit of. As capital N goes to infinity. So does that limit exist? Do you guys think it exists? It sometimes exists. What determines whether I'm allowed to just let this n right here blow up to infinity? Well, I already showed you guys what happens when you raise a number to a large power. It all depends on whether that number is bigger than 1 or less than 1. So that's exactly the criterion we need here. So if, and this is crucial, R, the common ratio, is a number that's less than 1 in absolute value, then we can let n tend to infinity, in which case, so the limit as n goes to infinity of the partial sum is the limit as n goes to infinity of that expression, c minus cr to the n plus 1 over 1 minus r. And if we're in this situation where the common ratio is smaller than 1 in absolute value, then this guy just disappears. It goes away, right? In the limit, this term goes to 0 in the limit. And we're just left with c over 1 minus r. So the infinite series converges. This is the value that it converges to. So in particular, let's do the c equals 1 case, because that's a pretty common one. So if c is equal to 1, then we get the following expression for 1 plus r squared off to infinity, and it's just equal to 1 over 1 minus r. There, that's a super useful formula, which I still use like all the time in the math that I do, and you guys will probably use a bunch of times in your mathematical career. And again, this is all only if r is less than 1. If r is not less than 1 in absolute value, you can get some really like zany results. So let me just show you like what could go wrong. So here's a little counterexample. All right. Yeah. So let let S be, how about 1 plus 2 plus 4 plus 8 plus so forth. So this would be a geometric series with common ratio 2. Then 2S, well, if I just double everything, so it's 2 plus 4 plus 8 plus 16. You might notice that's all the same terms as S except for the 1. So that's equal to S minus 1, if I could do that. But wait a second. So if I cancel an S from both sides, S equals minus 1? What? 1 plus 2 plus 4 plus 8 plus so on equals negative 1? No. That's crazy. There's no way that that's possibly makes sense. So what went wrong is, yeah, you're not allowed to just, basically I'm adding infinities and getting nonsense right here. So don't do that. So this is bad math. This is not equal, this is not equal. This is all junk math. So let's see, how about let's prove the pizza thing then, right? So here, if we were adding up, this was a half of a pizza, a quarter of a pizza, an eighth of a pizza. So let's make sure we get a whole pizza after adding all this stuff up. This is the geometric series of 1 over 2 to the n, starting from n equals 1. So let's see, how about, I gave you all these formulas. Usually I just remember this one, and I kind of factor things out so I can use it. So this is equal to, if I factor out a 1/2, 1 plus a half plus a quarter plus so forth. And notice I can use the formula because the common ratio is indeed less than 1. It's 1/2. So, according to this formula, this in the parentheses is equal to 1 over 1 minus the common ratio. Okay, so this is equal to 1/2 times, let's see, let's multiply top and bottom by 2. And I get a 2 over 2 minus 1. So this is 1/2 times 2. Which is 1 whole pizza. Good. So just what we hoped for. Yeah, Robert?
So question. So since you're making C1 in this case, if there was a 2 in front of the 1/2 n, would that not work with that formula, or would you just pull out the 2?
Just pull it out. Just pull it in front. Yeah, right. Yeah, which is what we usually do. Okay, let's see. I'll show you one more example of how to use this formula. One more neat example. How about, okay. How about this? So everyone knows that the number 1 is the number 1 is the number 1. 1 is 1 is 1. I have another way to write the number 1 for you. I claim that the decimal 0.999999, which is sometimes abbreviated as 0.9 repeating, I claim this is the same thing as 1. Exactly the same, no difference, right? I mean, kind of makes sense if you think about it, because if you try to think of a number between this and 1, you won't be able to. But now let's prove it. Now we can prove it. So I claim that this is equal to 1, and here's my proof. So 0.9 repeating, which is the same as, well, 0.9999999. So that's 9 in the 10th place, a 9 in the 100th place, a 9 in the 1000th place, and, oops, let me just factor out the 9 over 10. And I get 1 plus 1 over 10 plus 1 over 100, which is the same as 9 over 10 times 1 plus 1/10. This is 1/10 squared. The next term would be 1/10 cubed, and so forth. So this is a geometric series, actually, right, with common ratio 1/10, which means we can apply that formula over there. And let's see what we get. Well, it better be 1. So this is equal to 9 over 10, and now applying the formula, which is in that box over there, that's the same as 1 over 1 minus 1/10. Okay, so this is 9 over 10 times, let's multiply it by 10 over 10 here. We get 10 over 10 minus 1. So that's 9 over 10 times 10 over 9. Everything cancels, and we just get 1. Why do you think so? I thought so too. Yeah, it's pretty neat. So yeah, this is the 0.9 repeating, exact same thing as 1. Now maybe you understand that I could have also proven it to you if you believe that 1/3 is equal to 0.3 repeating. So just multiply both sides by 3. Get the same result. You can actually use this geometric series formula to evaluate any repeating decimal using what amounts to this same trick here. And, okay, there's one other thing. That's what I needed to say about this right now. There's one other thing I needed to say about series, but I want to say it in another context. Okay. Here's your last theorem from section 10.2. And I mentioned this before, but I didn't really make it official. So if you have a series that converges, necessarily the terms have to go to 0. Right? You can't be adding up a bunch of big numbers and expect to get convergence of an infinite series. That's just too much oscillation going on. This is the only way, if a series converges, necessarily the terms have to go to 0. Now, super common mistake by students that are learning this right now is to think, oh, I see my terms go to 0, so therefore the series must converge. Not true. So the converse is false. And so now I'm going to give you a counterexample. I said I would give you a counterexample, but I haven't yet because we didn't have the tools to prove that it was a counterexample. I claim that the sum 1 over n, which is 1 plus a half plus a third, and so on, I claim that this is a counterexample. Because clearly the terms do go to 0, right? 1 over n does go to 0 as n goes to infinity. But I'm telling you guys, this sequence does not converge. Oops, I claim that blah, 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 diverges is what I meant to finish, how I meant to finish that sentence. I claim this series diverges, even though clearly the terms do go to 0. In other words, this is a counterexample to the converse of the theorem. Now, the theorem I could prove, but it's just a short little 2-line proof. I think if you want to see the proof, I'll just direct you to the book. It's pretty short and easy. because I want to get to showing you that this is a counterexample, but there's still something else I need to do first to prove that that's a counterexample. Because don't believe me, don't take my word for it. But that, by the way, this series that I drew over here, my counterexample is a very special one. It even has its own name, actually. Anyone know what this series is called? This is the harmonic series. Yeah, for any musicians in the house, they might have heard about this. It's related to harmonic frequencies. Like when you strum a guitar, you hear the reason that a guitar sounds like a guitar and a saxophone sounds like a saxophone is because of the harmonics that play off that bass fundamental frequency. And they all happen to be in like fractions of the bass harmonic. So this is related to acoustics. So I'm going to refer to the harmonic series a few times, so you should know that name. Now, the thing that I said I needed to show you first is the first topic of 10.3. So this is, the title of this section is Convergence of Positive Series. So for this chapter, for this section, everything's going to be positive. We're not going to worry about any negative business. The picture gets a bit more complicated when you start worrying about negative, but for now, everything's going to be positive. Now, I want you to suppose that we have a series that you can write as some function. Right? We already talked about this situation before. So, in other words, there's some function, say, on the graph of y equals f of x, where the values at the integers agree with the sequence. And we're looking at the infinite series. So this will be a1 plus a2 plus a3 and so forth, which apparently is the same as f of 1 plus f of 2 plus f of 3. So basically I need the value right here, right? This is f of 1 right here. And then the value right here, that's f of 2. So f of 1 is the same as the area of this rectangle right here, right? It has width 1 and height f of 1. So f of 2 is the same as the area of this rectangle. F of 3 is the same as the area of this rectangle. So is this starting to look familiar? Yeah, this looks like a Riemann sum, adding up all these areas. Okay, it looks like a Riemann sum. That in itself doesn't prove anything, but as it so happens, it is like a Riemann sum. And the behavior of this sum is intimately tied in with the behavior of the integral. So in considering this series, you want to basically compare it to the integral of f of x, which since we're adding up all these rectangles off to infinity, we want the improper integral of f to x. Now, that improper integral of f of x, or here, let's start it at 0. How about? Now, here, that improper integral of f of x is all the area underneath this curve. maybe you can tell from the way I drew it that the area underneath the curve is bigger than the orange area. So the orange area is all these guys. The area underneath the curve is the red area. So I think I'm just going to do this proof by picture. So here, my proof by picture is, in this case, where, by the way, everything needs to be positive, I claim that the integral of f of x converges implies, so the integral of f of x converges implies that the sum converges. And I just proved it by my picture, right? Because like if the red area is finite, well then the orange area has to be finite too. It's smaller than the red area. But I could have drawn this a little bit differently. I could have drawn drawn my rectangles like this. Like forget about this first rectangle. Instead, let's make it like this rectangle, and this one, and this one. And now, the orange area is bigger than the red area. So in fact, this goes both ways. If this one converges, then this one converges. So in other words, this is a if and only if statement, or an equivalence. So the behavior of the infinite sum is identical to the behavior of the improper integral. If one of them converges, then the other one converges. If one of them diverges, then the other one diverges. Yeah, so they do the exact same thing. So now, I'm going to leave that as my proof. That's my proof by picture of this. And let's apply that to my purported counterexample, which, if you recall, is the function 1 over n. So what's the integral that I want to be comparing it to of 1 over x? So an equals 1 over n has, right, if this is f of n, so f of x is 1 over x, thus the sum, the infinite sum of 1 over n converges if and only if. Oh, by the way, do you guys ever see IFF? That means, yeah, if and only if. It's the same thing as putting the double arrows, actually. So this one converges if and only if this one converges. Converges. By the way, sometimes you might see me put the 1 here, or sometimes put a 0. It doesn't really matter because for series, we're only worried about the tail. We don't care actually what happens in any finite neighborhood. All we care is about what happens off at infinity. So it doesn't matter if I put a 1 here or a 0. It makes no difference. So what happens with this one? In fact, let me just put a 1 so we don't divide by 0. Anyway, we already know what happens with this integral. We could apply the p-test, for example, and we know that this diverges. But yeah, the integral from 1 to infinity of 1 over x diverges by the p-test, or you could just integrate it. Thus, the infinite sum also diverges. And, okay, so we now have our first counterexample to this theorem. And like I said, that's a really common mistake. Students think that just because the term goes to 0 means the series converges, but it's not true. So here's a count. Here, I have now proven the first counterexample to that. Okay, well, let's just continue in this vein. Let's see what else we can figure out using the integral test. So, similarly, using the integral test, we can get a p-test for sums, for series, right? And the result of that will be, well, it'll be the same as the p-test for improper integrals. So 1 over n to the p from, well, whatever, 1 to infinity. This series converges if and only if, you guys remember what we needed? The power 1 was the borderline case. Anything bigger than 1, and it converges. So this series converges exactly when the power down here is bigger than 1. Which is the same as the result for the integral from 1 to infinity of 1 over x to the p. Right? So we can now find lots of series that do converge as long as it's a power bigger than 1. So, for example, how about inverse squares? 1 plus a quarter plus a ninth plus a 16th, so forth. This is the sum of 1 over n squared. What do you guys think? Does this one converge? Who says this converges? Good, yeah, you guys are correct. This converges by the p-test that we just did. And just sort of kind of interesting factoid. This is a well-known series, and we know what it converges to. 1 plus 1 quarter plus 1 ninth, so forth. You add up all the inverse squares, you get pi squared over 6. Yeah, trip on that, right? It's like, well, where does that come from? This tripped me out the first time I saw it. I was like, what? How? Why? And you can prove this using Fourier series. There's a number of proofs. Like, you want to make it as a mathematician, find a new proof for this. But one of the proofs that I first saw was using Fourier series. Apparently, this was long suspected before it was ever proved. And it was Euler, the same guy who gave us Euler's formula. That was the first guy to actually prove this. Dude was a boss. He proved it when he was like 28. Like, he was a super genius. So, yeah, that's kind of interesting. This, another neat thing about this is that the proofs unite various disparate fields of math. Like, there will be a proof that number theorists use. There will also be a proof that analysts, like people doing Fourier series, Fourier analysis, use. Geometers would probably use a different proof. Okay. Oh, good. I might finish this on time. Okay, well, almost. So here's another theorem that you're going to use for your homework, which, by the way, I pushed back the due date until Thursday. It was originally due Tuesday, but I wanted to finish all this material before it's due. So this is the limit comparison test. I think it's just called the comparison test. It's like the comparison test. It'll remind you of the comparison test for sequences, but this is for series. So if, and again, we're only dealing with positive terms here. Let's say you have an, which is less than bn, then if the bigger series converges, that like forces the smaller one to also converge. Conversely, if the smaller one diverges, that like forces the bigger one to also diverge. It's kind of like, I don't know, if you swallowed an Alka-Seltzer and a bunch of soda and it like blew up, right? Like if the smaller one blows up, then the bigger one definitely has to blow up too. And if the bigger one is able to contract down to a finite value, then the smaller one definitely has to also. So let's practice using this. I'll show you an example of applying this. Okay, so how about let's do it for the series of 1 over the square root of n squared plus 1. Let's see if this converges. All right, so this is like, let's see, 1 over root 2 plus 1 over root 5 plus 1 over root 10, so forth. So from n equals 1, let's say. So what do you guys think? Any intuition on this one? Because you should look at this and, okay, you see the square here, the square root. When n is really freaking big, this 1 is kind of inconsequential. So when n is really big, 1 over n squared plus 1 is kind of close to just 1 over the square root of n squared, which is the same as 1 over m. So your intuition should say, here, I'll just put it approximately equal, that the behavior of this series should follow the behavior of this one. They're comparable, in other words. But, okay, let's see if we can compare them. And, okay, let me try to do this in 2 minutes. So, what's our guess then? Based on this fact, do we expect it to converge or diverge? Diverge. We expect this to diverge. Let's try to compare with 1 over n. So let's see, n squared plus 1, this is bigger than n squared. So the square root of n squared plus 1 will be bigger than the square root of n squared, which is the same as n. So if I flip both sides, 1 over the square root of n squared plus 1, is less than 1 over n. Why does this not help me? Yeah, so, okay, great. So I found that it's less than a series that blows up to infinity, right? So like if I sum this, it's less than the sum of this, but this is infinity. So that tells me absolutely nothing. Like, great, I'm less than infinity. Well, yeah, I already knew that. Okay, so this didn't help. Right, this is infinity, so that doesn't help. But maybe I can compare it to something else. So how about, okay, so this was not a useful inequality. What about, let's see. I want to compare it to n squared plus 1 how about, is it true that is that true? Let's see, if I square both sides, I get n squared plus 1 is less than or equal to n squared plus 2n plus 1. So let's see, cancel the n squareds, cancel the 1. 0 is less than or equal to 2n. That's true. Okay, good. So this is true. Right? I can erase this question mark. This is a true inequality. So 1 over the square root of n squared plus 1 will be greater than or equal to 1 over n plus 1. So this sum will be greater than or equal to this sum. But this, let's see, this is actually the same as the harmonic series, just starting at 2 instead of 1. So what do you think happens with this one? Yeah, this diverges too, right? Like, so what if I started at 2 instead of 1? We already know that 1 plus 1/2 plus 1/3 ... We already know that that adds up to infinity. Well, this just started like one term later. So what if we drop the 1? You're still blowing up to infinity. So this series still clearly diverges, but just based on that observation. Therefore, the comparison test tells us that this diverges too. So comparison with the sum of 1 over n plus 1 gives us that our series diverges. All right. One more theorem in this section that I'll have to do on Wednesday.